Let's talk about confidence interval in more detail, and as an example I would use a proportion case. So I'm trying to estimate population proportion P. I'm assuming I have this population, whatever it's about. It's a binomial nature, and it has a specific topic that I'm interested in. Like if somebody likes something or dislikes something, or people's opinions or people's behaviors. And there is no way for me to figure out the overall people's opinion about something because population is too big, or sometimes it's infinite and I can't really ask everybody to get their opinion. What I can do instead is get a sample of certain size, and I need to make sure that that sample is nice and random and it's not too big and not too small. And we'll talk about what all those things mean. And I can ask people in the sample the same question and count how many replies of a certain answer I got and calculate a p-hat, which calculated by counting how many responses on a certain topic I received out of my sample. Theoretically, I can get any sample of the same size, and I can get lots of different p-hats. And all of those p-hats would be a little different because samples vary and p-hats vary, which means that p-hats, if I put them all together, they create kind of their own distribution. So all of these numbers right here on this axis is all the different opinions for different samples, but they all relate to the same topic in the population and the same overall opinion. So the question is, what does this p-hat distribution look like? What does it has to do with this population distribution? And all of those things were addressed in Chapter 8. If you have a random sample that's not too big, meaning the sample size is less than or equal to 5% of the population size, and not too small, meaning n p-hat 1 minus p-hat is greater or equal to 10, so these are the boundaries of the sample size, then this p-hat distribution would be approximately bell-shaped. And 95% of the time, if we use 95% level of confidence, we will get p-hats that will fall in here, inside this interval. Some p-hats will fall outside this interval, but we're 95% likely to get the p-hats from here. This distribution also, according to the Chapter 8, will have a center at p, which is the number that's exactly that I'm after, because I don't know what it is and I'm trying to estimate it. I also know that the standard error of this curve, sigma p-hat, can be estimated or calculated with p-hat 1 minus p-hat divided by n. So the question is, how do I construct a confidence interval? How do I pick just one p-hat from one sample and get a good confidence interval? I don't know if I'm going to get a good confidence interval actually, or if I don't, but I know that 95% of the time any of these samples, any of those p-hats, will be right here inside this interval, which means that I'm very likely going to select a good p-hat, and the size of the interval, which would be controlled by this level of confidence, would be sufficient enough to estimate the p. So how's it done? Well, you use one of these p-hats, which somewhere here 95% of the time, and you construct this size interval around it. How do I know what size this interval is? Well, if this is 95% confidence, then according to the z-scores, this interval would be 1.96 standard deviations out. What does it mean, 1.96 standard deviations out? It means that from this point to this point, from the middle, it's plus minus 1.96 standard deviations of that curve, which is our standard errors, out would be this size of this interval. And because we're building it around p hat, that's going to be our center. And that's how we calculate our confidence interval. Now, why am I using p hat? Because that's just what I know, and that's my point to estimate. And I know the p hat is somewhere inside of this interval, around the p. So that means p would be part of this interval built around the p hat of this size right here, 1.96 sigma p hats, which means that your formula for your confidence interval, 1.96 in this case, of these standard deviations out. And more generally, 1.96 will be replaced eventually with z, and z-score will depend on whatever this area is. It's not always 95%. It could be 90, 99, 98%. We're building one of the possible intervals. You can build lots of intervals based on lots of different samples and lots of different p hats. We're only building one specific interval. And we can say with 95% confidence that this p would be inside this interval, because this p hat is 95% likely to be here in this interval also.